Welcome back. Let's do coin change today. You're given an integer array coins representing coins of different denominations and an integer amount representing a total amount of money. Return the fewest number of coins that you need to make up that amount. If the amount of money cannot be made up by any combination of coins, then return -1. You may assume you have an infinite number of each kind of coin. So this is a dynamic programming problem that's pretty common. If you keep taking algorithms classes, it's going to come up eventually in this exact form. Yeah, like verbatim in this exact form. The amount of runtime is actually going to be not polynomial due to it being related to this amount value. It's pseudo-polynomial because amount is it's a value instead of a size of a runtime. So it's going to be O of amount times something. In this case, O of amount times O of the number of coins. So the size of coins times the value of amount. And since value could be anything, it's pseudo-polynomial on the number of bits used to represent amount, if that makes sense. Let's get into the algorithm itself. It's dynamic programming, so we're going to need an array to keep track of previous values. So let's use that as a vector. So vector of integers, and I'm going to call it t. What do we need t to be? It's going to be a one-dimensional. So how big we want it? We want it to be amount plus 1 in size, 0 for the base case, and then up to the amount of value itself. So if it was only the size of the amount, we due to 0 indexing, it actually the highest value representation. So if the first element's for the coin value of 0, second element's for the coin value of 1, and then the final element should be for the amount of value. The gist of it is going to be we increment. So if amount were 0, how many coins do we need? 0, that's our base case. If amount were 1, how many coins do we need to add up to the amount 1? And then 2, and then 3, and then 4, and then 5. And we're using previous entries in this table amount to eventually calculate the final element. So amount plus 1 would be the entry in the table corresponding to the actual value of amount. And what we're going to do is we're going to constantly compare against, say, an infinite number of coins. So you need some default value. I'm going to show you a C++ library that I think is pretty essential, and it's called numeric limits. Numeric limits. And you feed it a template argument for the data type you want, and then it gives you a namespace, and you can call stuff like max or min. Those are really the main two you need. In this case, I'm going to use max. And I think this is more not intuitive. This is more generic to use than something like int max, which is another macro that's built into C, C++. Actually, int max you can use in C as well, I think. But in C++, I think this is easier to remember, because then you can start doing stuff like double and float and weird other types too. And I think that's easier than remembering specific macros, although float max, I don't know if that resolves to anything. Float max. Well, it would have to be a float. It doesn't look like it. I'm not seeing syntax highlighting for it. But if we have int max, oh, that doesn't syntax highlight either. Anyway, I think this is easier to remember because it's more flexible of a syntax. Anyway, so this is our default value. So we're going to initialize all of our elements to that, except for the first entry, which is going to be our base case. So t of 0 is 0. It takes 0 coins to add up to the value of 0. So now we've got that set up. Let's do our main dynamic programming loop. it's 4 int I equals 1. So since we got this base case hard-coded, we're going to skip that and start at 1. I is less than amount. Actually, less than or equal to it. And then plus plus I. What this is doing is we're having the amount value that we want to add up to also correspond to the index in our dynamic programming table. So all the way up from 1 to the amount. How do we do that? There's a couple of things. We're going to take the previous entry is going to be, so for each of the coins, 4, and then our coins is integers, so int c in, oops, don't want a walrus symbol, I want c in coins. For c in coins, what do? The number of coins to add up to a particular element, for each, we look at each particular coin, and if, so the current value minus the value of the coin, that entry of that table plus 1. So minus the value of the coin, then you add in 1 coin with that value, so that entry in that table plus 1. That's how many coins it takes to add up. And we're going to look at each coin in turn and take whatever the smallest number is. It adds in, I think, a constant speed up time if we actually sort the coins first. That would add in another n log, let's say c for the number of coins that we have. So n log c to sort it. So I'm going to add in that line and then think about if I want to keep it or not. So sort coins dot begin, coins dot end. And now our coins array is definitely sorted because it doesn't mention that the coins are sorted. The examples show that they are, but I don't think that is for every single input. So now we're going to assume that they are sorted. So back to our loop, we want to make sure, let's first do a bounds checking. So if I minus the c is less than 0, we want to break out of the loop. This lets us do a break instead of the fact that these are sorted lets us break instead of continue, so then we don't have to look at the remainder of the coins. That's our constant time speed up. It's not going to change the asymptotic value, but it could it does add a little bit of real world time, wall clock time improvement. All right. Skipping any indexes below 0, that's just a bounds checking error. And then the next is t of I equals the min of itself, or let's see, what would it do? Min of itself, or t or one more than the t of I minus c. So the current value, looking back at if you were to add in this coin from a some previous element, so the current value minus this coin, however many coins that takes, plus 1. So adding 1 of this coin, adding 1 to that. If that's smaller than this, then that is how many coins we can use. And there's a condition on this. We would do it if, well, that might be fine. I'll give that a, I can't put my finger on what's might be an issue with this, but I think that might be okay. And then we finally want to return the last element of our table. Let's write out run times and do an example, and hopefully that's got everything in it. So runtime, first we have this n log c, so it's O of n log, c log c, c for the number of coins, plus What else do we have? That's constant. This is O of amount to initialize. O of amount. And then we do an O of amount times an O of C loop plus O of amount times C. So O of amount loop and then an inner loop, O of C. This will happen, but this isn't going to change, say, asymptotic complexity. And then this is an O of 1 operation, assuming the table is random access lookup in constant time, which it is because we're using a vector. So then there's that, and then O of 1, a constant return value. And then looking at this, this cancels out because this strictly dominates it. And then we can't be totally sure which of these will dominate. If amount is small, that would make this thing small. But if the C is bigger, so if amount is small and C is big, this would be kind of this. If amount is small enough, this would become smaller. So I think we really do have to leave the runtime like this, unless we remove this sorting step. I think this is as simple as it can be. This is polynomial because this is on the number of coins. This is not polynomial. This is NP hard because of this amount value. And it could be anything, it could be crazy. But yeah, this is not a polynomial time problem. Let's do an example. Let's just do example number 1. All right, so input is 1, 2, 5. And that's already sorted, but so we are going to sort it again. So 1, 2, 5, that's it. And then our amount is 11. Ooh, do I want to do that? Well, let's start with the table and go from there. So 0, 0, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11. Base case 0. So we sort our array, it's already sorted. And then we have this numeric limit. Let's just say that's infinite. So I'm going to just do a plus sign for infinity, although it's not actually infinity. It's going to be an integer value, but it doesn't matter. So our base case is 0. So starting from 1. I less than the amount, yep. And then for each coin in coins, if I minus C, so if 1 minus 1 is less than 0, it is not. So we can we don't break. We continue and we hit this line. So then T of 1 is the minimum of infinity, or 1 plus Ti minus C. So 1 minus 1, so that would be infinity versus 1, that is 1. And then let's continue on. Oh, you know what? I didn't account for in the return statement. If it's infinity, then we want to return minus 1. So there is going to be a conditional. So it's if the back element is this max, and that's part of why I saved it off into like a local variable instead of keeping it as this function call, because that's just smaller syntax. So if it's the maximum, then we're going to return minus 1. Otherwise, we return t dot back. That's a conditional. You could handle it as a, well, no, you couldn't do that as a min. So you pretty much have to leave it as something like this, some kind of conditional check. All right, so we're back on loop 2. So I is 2. If 2 minus 1, oh, sorry, after we set this to 1, we were going to continue on and look at 2. I minus 2 is negative 1. So then we break out of this inner loop. So that's the why I didn't look at the rest of it. All right, so now if I equals 2, we're going to have infinity. Well, first of all, 2 minus 1 is 1. So we're going to look at this guy. So we're not going to break. It's not below 0. So infinity versus 1 plus 1. So 2. And then we look at the next iteration of our loop. 2. So 2 minus 2 is 0. So now we're going to look at the minimum of 2 or 0 plus 1, which is 1. So we're going to make that smaller. Next iteration of the loop, 2 minus 5, that is less than 0, so we break. All right, next element of the table, we're looking at 3 minus 1, that is not less than 0, so now we're looking at the minimum of infinity, or 1, so 3 minus 1, which is 2. 1 plus 1, well, that would be 2 coins. So 3 minus 1, next iteration of the loop. Now we're looking at 3 minus 2, so C is 2. That's 3, 2, 1. So this one, that is also going to be 1 plus 1. So we're looking at 1 versus 2. No, sorry, 2. The current value there is 2 versus 1 plus 1, which is 2, so that's not going to change. And on the next iteration, we're gonna break. I might cut the example short here because this is kind of tedious, and 11 is a pretty big number. Or I'll speed through the rest, I guess. So 4, it's gonna be. Let's look at 4 minus 1. So that's 3 plus 1. That is doable. So that's gonna be 3. Versus 4 minus 2, so 2, we have a coin that's 2, you can do 2 of those. And I think that's the minimum you can do for 4, because you can't go back 5, or 1, 2, 3, 4, no you cannot, that's it. And then 5, so 1 before plus 1, that's going to be 3. 2 before plus 1, 1, 2, that is also 3, or 5 before plus 1, 1, 2, 3, 4, 5. In this case, we are down to 1 because we have a 5 denominational coin. And that helps. 6, 1 before plus 1, that is 2. 2 before plus 1, that is 3, so that's not going to improve our score. And then 5 before plus 1, that's this one, plus 1, that is again 2. That's not going to change. 7, 1 before plus 1 is 3. 2 before plus 1, so 1, 2. That is going to be 2. That's going to improve our score. So that would be like a 5 coin and a 2. And then 5 before plus 1, so 1, 2, 3, 4, 5. That is going to be 2 again, so that's not going to change our result. 8, 1 before plus 1 is 3. 2 before plus 1 is again 3. And then 5 before plus 1, 1, 2, 3, 4, 5. That's again 3. So that's the least we can do for 8. 9. 1 before plus 1 is 4. 2 before plus 1 is 3, so that's going to improve our score again. And then 5 before, so 1, 2, 3, 4, 5. That is 3 again. So 5 before plus 1, which is 2, plus 1 is 3, not going to improve. 10. Let's look at this 10. So 1 before plus 1, that's a 4. These two are the same, so that's not, so 2 before plus 1, that's another 4. It's not going to change. And then with 5 before plus 1, 1, 2, 3, 4, 5, that's a 1. So 1 plus another 1 is, 2. And that makes sense because we have a 5 denominational coin. You can use 2 of them to reach 10. And 11 is going to be, our target is 3. So we're looking at 1 before plus 1. That's a 3. 2 before plus 1 is 4. That's not going to improve our score. And then 5 before plus 1, which is going to be 6, plus another 1 is 3. So that would be, wait, 1, 2, did I count that right? 1, 2, 3, 4, 5. So 2 plus 1 is 3. That's not going to improve our score. And then that's the end of the loop. So then we would break out the loop. And what do we do next? We look at this last element. It is not still infinity or integer max. So we're not going to return -1. We're instead going to return the value. And that is our solution. That looks correct. I'm going to give it a run. Hopefully I didn't miss anything on here. Oh, typo, coins, COINS. C in coins. What did I miss here? Cannot represent type of integer. Solution. T of I, 1 plus T of I minus C. What? Characters. I'm not using characters. Oh, signed character overflow. Got it. So how do we do this? Signed integer overflow. So that's gonna be something like, I'm gonna see, if I want to see is less than 0, it is not, so we're not indexing incorrectly there. 1 plus, oh, because we're at the integer max. What I'm going to do is maybe I'll initialize with 1 less than integer max, so we can actually either this or doing some comparison check on if the value in there is not currently integer max. I think this will work. Let me see if this works. So this is leaving room to actually add something. So then it's not technically infinity, but as long as our maximum allowed value. So the coins, the maximum of a single coin, so wait, maximum amount, so 10 to the 4th. That is much, much less than 2 to the 31 minus 1, which is a signed integer maximum, meaning we can definitely, as long as whatever our initial value is higher than this, then we're good. Because for that would be, we need something that would always lose the first time it's compared as a minimum versus something else. Yeah, that's fine. So the value of coins is, that should be good. That's fine. I think that's fine. So let's give that a run for our submission. All right. Golden. Now let's mark it off, and you guys have a beautiful day. Thanks.